All right, so we're going to take a look at continuity properties. So, with continuity properties, if you have two functions that are continuous on the same interval, so, you have g of x on one interval and then f of x on the same interval, then their sum, difference, product, and quotient are continuous on that same interval, except for any x values that make your denominator equal 0. That is primarily going to happen here on the quotient piece. So when you are going through these and you're trying to determine, okay, so are these going to be continuous or not, and where they're not going to be continuous, if you ever have one that has a denominator and that denominator can equal 0, if it equals 0 on that specific interval, then you're not going to be continuous over that interval when you combine them back together. So, I know I said there's 4, so here's your sum, there's your difference, there's your product, and here's your quotient. This one here, this is called a scalar. What a scalar is basically saying I've got a function f of x, and I'm going to multiply that function times 3. So what I'm really looking at is like 3f of x. So that's what this is. On this one here, this is you have your f of x value. The only thing that you need to be aware of is when your n is greater than or equal to 1. So as long as your n is greater than or equal to 1, then you're going to be continuous over that whole entire thing. If you have a fraction, so you're less than 1, you could wind up with a root value, and that root value could not actually exist on the actual function itself. So that's one of the reasons why we want to make sure that that n value is greater than or equal to 1. All right. So let's talk about examples of types of continuous functions. So anytime you see these continuous functions, these are automatically continuous. There's nothing you need to do because all of their domains are all the same thing. They're all real numbers. So the first one, the constant function. So basically you have a horizontal line. For the next one, the integer n is bigger than 0. So that's basically any type of continuous function here. This will be continuous. So as long as that n is greater than 0. A polynomial function that's continuous for all x. A rational function that your denominator basically can't ever equal 0. So like x squared plus 9, x squared plus 15, things like that. Your denominator will never equal 0, so you don't ever have to worry about that one. If you have an odd root, then you will be continuous. And if you have an even root, it's continuous wherever f of x is continuous and non-negative. So we want to make sure that the root on an even one, that the inside never goes to a negative number. So as long as you don't hit a negative number, then you will never be discontinuous, because then you would have an imaginary number if you did that. Okay. So let's take a look here. So these are what your problems are going to look like. It's going to say determine where each function is continuous. So they give you a f function and a g function. So we're going to look at these separately. So if I'm taking a look at the first one here, this f of x function, you're going to notice that this is kind of an ugly problem to look at. So what we want to do is we want to take this and we want to break it down into something smaller. So if you notice, I can say I'm going to let my f of x equal x squared plus 5. And I'm going to let my little g of x equal x over x squared plus 4. So that way I can take a look at these separately and then come back and say, okay, my answer is going to be yes or no. So if I'm looking at the first one, I notice I don't have any fractions, I don't have any restrictions, so I am continuous everywhere here. If I take a look at the second one here, I only care about the denominator. So when I'm looking at the denominator, I'm saying, okay, is there anything that's going to force this denominator to equal 0? The answer is no, so I'm going to be continuous here as well. And then so if you look at this, I've got f of x minus g of x. That makes this really big f of x problem up here. So since this one is continuous and this one is continuous, my big f of x will be continuous. So this is just an easier way for you to take the problem and break it down into something smaller so you can take a look at it to make sure that what you're looking at is actually going to be a true thing. Okay. So try the next one. I'm going to put you on g of x here. I'm going to give you a few moments, hit the pause button, and see if you can determine that are you continuous over this whole entire domain or not. Okay. So hit the pause button now. All right. So let's take a look at what we just did here. Okay. So I'm going to, again, let my f of x equal x cubed plus 2x. And then I'm going to let my g of x equal the x squared over the x squared minus 1. And so what I'm looking at is f of x minus g of x. So I notice on my first one here, I am continuous everywhere because, again, I don't have any specific restrictions or anything else on this. So I am continuous here. So looking at the second one, however, there are numbers that can make that denominator equal 0. And since there are numbers that can make that denominator equal 0, then I've got a small problem here and I need to deal with that. So what I would do is I would say, okay, I am not continuous when x is equal to 1 or negative 1. Because again, remember, I'm only looking at the denominator piece here. So to write this answer, g of x, so we're looking at for all values of x such that x cannot equal negative 1 or 1. So that's when you're talking about am I continuous, and the answer is no, I am not continuous. I do have breaks. You're going to put it in some format that looks like this. Okay. So when you're talking about determine or whatever the function is continuous or not, this is what it's looking for. It's looking for something along this line where it says that yes, I am continuous. Or you're going to look at this line where it says, no, I'm not continuous, and here is my reasoning for why I am not continuous. So keep that in mind as you do those problems. All right. So let's just kind of talk about continuity of other things, because there's just there's a few things out there where things are not continuous or they are continuous that, they're big, but they're not really they're not big enough to host a whole entire, talk about it. So let's take a look at it. Continuity of a composite function at a specific point. So if you have a composite function, and that is going to be the f of g, so that looks like, when you're actually writing this out, it looks like f of g of x. If g is continuous at a and f is continuous at g of a, then the composite function f of g of x is continuous at a. So basically what we're doing is we're going to look at our g function first, because that's going to be what we're focusing on here. And we're going to find out, am I continuous at that function? And if the answer is yes, then I take that value and I plug it in, and then I reevaluate it again at f of x. And if I'm continuous at f of x at that specific function value, then when I put them together and compose them, then I'm going to be continuous over the whole entire thing. So when you're looking at limits, so focusing on just the limit piece of this, I want to look at on the first one, if G is continuous at A and F is continuous at G of A, then this is going to be a true statement here. That means the limit as x approaches A of f of G of X is the same thing as saying that f of the limit of as x approaches A of G of X. So basically, if my limit of G of X exists at A, then I can take that value and put it back in to my f of x value, and I should be able to be continuous at that as well. So there is really no difference between the two of these. It's just the wording, because then it talks about the limit. And so that's how you're going to relate the two together. Is basically what you're saying, the y value for G is going to be the x value for X, which is saying that the limit for G will be the X value that we're going to focus on to get the actual limit of the whole entire thing. Okay. So let's talk about pieces of functions. So we have left and right continuity. And so if I'm looking at this and I want to know, well, am I continuous over the whole entire thing? Well, the answer is no, I'm not continuous over the whole entire thing. But if I'm looking at this, I am going to be continuous here at A going towards B. So this is called a right continuous at A, because I am starting at A and I'm going right. And so I'm continuous here. I'm not continuous here, but I am right continuous. So as I go right, as I go towards B, I am continuous all the way there until I get to the B value. Left is the same thing, except it's backwards. So I'm left continuous, but now I'm going to be at B because I'm coming off of B and I'm going towards my A value. So I'm going towards the left. And so because I'm going towards the left, I am left continuous at B because I start at B and I know what B is. But as I move towards A, I am not continuous at that function. So again, one more time. So when I'm looking at a right, I know I'm starting on the left-hand side, but I'm moving right. That's why it's called a right continuous. And when you're right continuous, the leftmost value is what you start at and include, but you never include the end value. And if you're left continuous, that means you're starting at the most right-hand value and you're moving left. So the left and right is the terms of how you're moving on the graph itself. Definition of continuity at endpoints. So this just kind of go back to, I showed you the visuals. So this is actually like the wording of it. So when I'm looking at this, I'm looking at, here is my right-hand side. Notice the plus sign above it. And then here is my left-hand side, but notice that instead of an A, it's a B. And I've got the little negative that's telling me I'm coming from the left-hand side. So that's just when you're looking at limits, that's what you're talking about. That should tell you where you are going to start at. Okay. So if I'm looking at this graph here and I want to talk about my continuity, because this is what's going to happen. You're going to be given a graph and it's going to say discuss the continuity on this graph. This is what I'm looking for. I know that, well, okay, I'm defined here at this point. I'm not defined here at that point. So I know if I focus on this piece here first, I'm going to wind up looking at a left continuity because I'm starting at my B value and I'm moving in this direction. And so I'm going to be continuous from negative infinity to 0. And I'm going to include that 0. So this here is my left continuity piece here. as I move forward for this and I keep on going with the graph, I have to remember that I am not defined when I go to the second piece up here. So I have a parenthesis, but I'm going to start at 0, but I have a parenthesis and I'm going to run off into infinity. So I am not right continuous here. I'm only left continuous. We primarily talk about left and right continuous again on piecewise functions because when we're dealing with piecewise, we're dealing with pieces of a graph. Because if you look at this, this here looks like a parabola and this here looks like a straight line. This could be an absolute value and this could be part of a cubic. We don't know. But the point is I have two different functions here. But at some point here where they're going to start and stop, I've got this thing right here that's happening. And so that's what I want to look at, my left continuous and my right continuous. When we talk about roots, roots are when you have fractions. Okay, so whenever you have a fraction, there are some places on here that you're not going to be continuous at. What you want to remember is this piece right here when we talk about where basically are we going to start and or end at, because remember, for your even roots especially, you have to be bigger than 0. You cannot have any negative roots, because if you have negative, like the square root of -9, that doesn't exist, because that's going to give you an imaginary number. And so when you're dealing with these, you need to make sure that whatever that y value is greater than 0. Okay. If it's an odd integer, then the good news is if it's an odd integer, you're going to be continuous at pretty much all points. But however, if you are even, if that n is even, you do have those restrictions, and those restrictions are what make you have imaginary numbers. Okay. So if you get imaginary numbers, you are not continuous. All right. So this is just an example of looking at continuity over a square root property here. So remember I told you, so if I plug a number into this piece right here, if I plugged in, let's say 4, that'd be 9 minus 16, which would be -7. -7 winds up being an imaginary number because I'm outside of this piece here on both sides, because remember there's a plus and a minus for both, and so that's not going to work. So I have to look at where I'm bounded at. And if you take a look here, mind you, square roots can be equal to 0, so that's absolutely okay. So I am right continuous at -3. So that basically means I can start at -3 and I can move forward in this direction here. And then I can turn around and say, okay, well, then I'm going to look at 3. I am left continuous at 3 because I can start at 3 and go left. But notice I'm not left continuous at -3, because if I was left continuous at -3, then I would be able to continue on to my graph, and there's nothing for me to continue on to. So I cannot be left continuous. I am only right continuous. And to remember, when you are continuous, left or right, it's the direction that you're moving in. So I was moving right on that one, and I'm moving left on this one here. Okay. So that's what it's talking about when it's saying, am I left or right continuous? That you are going to be looking at how am I moving on these specific functions. And on a function like this, you actually have to look at left and right continuity. Continuity over trig functions. So here's the key. All trig functions are continuous at all points in their domain. So if you have a function and it has a domain, everywhere that you're not restricted, then you are able to be continuous at all the points that are in there. So the good news is you have sine and cosine of x. You're always going to be continuous 100% of the time right there at sine and cosine of x. But then you have tangent of x. Well, tangent is our first place that we say, okay, where am I not continuous at? And so if you're thinking about tangent, tangent is the same thing as sine over cosine. Well, my cosine is 0 when I have pi over 2 and 3 pi over 2. So I am continuous for all values on this unit circle for tangent, except when my x values equals pi over 2 or 3 pi over 2. For cotangent, the same thing as tangent, except now I'm not looking at sine. Looking at cosine, I'm looking at sine, because remember, cotangent is cosine over sine. Well, sine is 0 when it's pi and 2 pi. So I am going to be continuous on all the points except when I am approaching pi and I'm approaching 2 pi. So keep that in mind when you're doing these. And it's also their multiples. So if you think about this here, I've got a k value. So my k, pi over 2 when k is odd. And then for my sine over here, I'm looking for all values where k is greater than or equal to 1. And that's going to be k pi. Sounds like a pop group. When I'm looking at secant and cosecant, well, you have to remember that secant is 1 over cosine. So this is also going to hold true for secant. And then cosecant is the same thing as 1 over sine. So this is also going to hold true for cosecant. Okay? So when you're looking at these, we want to make sure that you understand I'm continuous at all their points in their domain except where I have my vertical asymptotes, where my denominators equal 0. And this is how you remember them. Okay, so it's primarily, oops, forgot about that. Primarily these ones here when you're looking at these. Okay, so then this just kind of reiterates of what we're looking at. So on your sine and cosine functions, there are no breaks, there are no gaps, so you're going to be continuous everywhere. This here is a secant one. So if you look at the secant, notice I have these vertical asymptotes here, right here at all these odd values. So you just kind of want to make sure that when you're looking at these odd pi values over 2, that you understand that that's going to be where you are not continuous at. All right, so those are just random properties for other stuff on continuity that you just need to know and be aware of. And so you'll apply those when you're actually doing these problems. So now let's talk about the intermediate value theorem. You need to highlight this somewhere in your notes because this is extremely important. This is one of like 3 theorems that you will need to prove, especially on the AP exam, that you will need to prove, and you will need to understand it forwards, backwards, upside down, whatever else. This is extremely, extremely important, okay? So let's talk about what it actually means. The intermediate value theorem. So suppose I give you an interval, okay? And there's a limit that basically are my y values that are on that interval. Then what it's saying is if I pick something else here on this interval and I call it C, then f of C as long as it's between A and B, will also exist, and it will be on that limit. So it's just saying that if I've got an interval here and I pick a number in the middle, so let's say I've got an interval from 0 to 5, and I'm continuous from 0 to 5. It's saying if I say, okay, if I'm continuous from 0 to 5, if I pick my C value to be like 2.2, that's saying that since I'm continuous from 0 to 5, and I can have a limit anywhere on that, I'm also going to have a limit at the value C 2.2. I'm actually going to have a limit there. That's all the intermediate value theorem is saying, is that as long as you're continuous over this specific interval, this is what's going to happen. Okay. Also, if the function is continuous over a certain interval, then if x takes on all values between a and b, then f of x must take on all the values between f of a and f of b. Remember, f of a and f of b, those are your y values for your respective a and b values, x values, okay? So that's all this is saying. It's just saying that regardless of the interval that I choose, if I give you these x values, I'm going to have these y values to go along with it. And notice it is closed. That is the key thing. You cannot have an open interval when we talk about the intermediate value theorem. It has to be closed. That means there's no open parentheses. That means there's no infinity signs. It has to be closed. So that basically means that both A and B have to be defined. So if I'm looking at the intermediate value theorem here, this is saying I am closed here and I'm closed here. So if I pick some random value, and if you notice I have, I'm defined all the way between my two closed values here. If I pick some value C that's in between A and B, I am actually going to have a limit at that point here on this interval. And if you notice, I can pick multiple C values as long as I'm in between A and B and A and B is continuous, then I'm going to have multiple values on this interval here that I can pick that can have the same limit or that will exist. Okay? And that's the key. There's at least one number. It can be more than one number if it needs to be, but it's just one number. Okay? If I'm not continuous from A to B, so if you notice here I have a break, then there's going to be no such number C in here. So I might get lucky and pick a C value here, but what happens if I get unlucky and I pick it here? Well, the problem is because I pick it here, notice this big, huge gap right here between that point and that point there. So that means those limits, they don't exist anywhere on this interval. And if you take a look over here, if I pull these numbers over, I've got this full entire range value here. Let me change a different color. This full range value that's sitting right here doesn't exist, and I have that break. And so therefore I am not continuous because there's not all my y values have a home. I'm missing some y values, and I'm missing those said y values right here at this specific point right here. Okay, so we're not continuous, and so therefore we're not going to have a C. We can't put a C value on here because there might be a possibility that I might run into this piece right here. Okay. What's nice about IVT, intermediate value theorem, so you're going to hear me say IVT a lot because intermediate value theorem over and over again, I get tongue-tied. So IVT is often used to locate zeros of a closed function as long as that interval is closed and it's continuous. So basically what I'm looking for, the key thing on this one is right here. There has to be a sign change. So if you have an interval from A to B, And if you evaluate A and then you evaluate the endpoint B, and one of them is positive and one of them is negative, you've had a sign change, which means you've crossed the x-axis, which means there is a 0 somewhere on this interval here. So let's look at sign charts, because sign charts actually help you with this. So you are going to use sign charts a lot later on, probably in a few weeks when we start really getting into derivatives, because we'll start talking about graphing analysis and stuff. So I'm going to introduce them to you now, but we're not going to use the full spectrum. We're only going to use a piece of it, because all I want you to do is get acclimated to sign charts. So that way we can first determine if we have any zeros at all whatsoever. So when we talk about sign charts, this is going to be a tool that we're going to use to analyze graphs of functions, or for even solving inequalities, but we're not really worried about inequalities right now. What we're going to focus on is, do I have a sign change to see if I have any zeros or anything. Later on, we find where the function is 0 or undefined, and the partition number, we're going to take our line that we're going to have and we're going to partition that line into those intervals. Right now, today, the only thing that we're going to focus on is going to be where the function is 0. Undefined will come later on. So we're going to talk about that later on, but today we're only going to focus on where the function is 0. We then test each interval to determine if the function is positive or negative in those intervals. And so we'll talk about that again later on. But again, this is just to get you acclimated to use of a sign chart. So when we construct a sign chart, so for all we're doing today is we're going to focus on part B here. So we're going to find all the numbers for today where points of the function is 0, where the numerator is 0 if there's a numerator, but the denominator is not. So we don't care about the denominator for this specific part. Then what we're going to do is we're going to plot these in a number line. And then we're going to take numbers and we're going to test to see if there's actual sign changes or not. Okay. So let's take a look at the first one. So we're going to use IVT. So notice there's no fraction here. We don't have a rational function. So this one is actually a really simple one to be able to do. So because there's no fraction, there's no need to build a sign chart. But what I have to do is I have to evaluate. I have to evaluate for when f is equal to 0 and when f is equal to 1. Because I don't have any restrictions I have to deal with or anything, and I don't have any other things I have to focus on, I can actually take a look at this and see what's going on. So if I look here, when I plug in my 0 value, I get 0 cubed plus 2 times 0, I get -1. When I plug in my 1, I get 1 plus 2 times 1 is 2. So 1 plus 2 is 3 minus 1, I get a 2. So notice my sign change here. So because I have a sign change from 0 to 1, I have a yes, there is a 0 on the interval 0 to 1. And here's the key. If you want full points by IVT, you have to make sure that that's in there. If you are trying to tell me that yes, that there's a 0 and it, that's on this interval, if you leave out by IVT and you say because of the sign chart, that is not good enough. The sign chart does not give you credence to say yes, there's a 0. What gives you the credence is going to be the IVT. So you have to make sure that you put the intermediate value theorem in there to say, yes, I use the intermediate value theorem because that says if there's a sign change from point A to point B, then I have a 0 on that interval. Okay, so be aware of that. You have to you need to highlight this, you need to mark this, you need to do something that makes this piece right here stand out. Put a bunch of stars by it, make some arrows, tattoo it on your forehead, something. But make sure you understand that when you have a sign change, you have to say by IVT. It's that important. All right, so let's look at another one. What if they don't give you, this case they did give you one. So that I've got this interval here. Oh, I've just set off Bixby. Sorry about that. I've got this interval here that is from -10 to 10, and it's asking me if there's at least 1 0 on this interval. Okay, and so what I need to do here is I need to, in this case, you can set up a sign chart if you want to. So we're actually going to set one up here just so you can see how it's actually going to work. Okay, because I'm actually going to have a couple of different things here, because I'm actually going to have more than one thing that I'm actually going to look at. Because if you think about this, I could potentially have 2 zeros on this interval. So the first thing we're going to do is, typically we would start here, but because I'm not talking about discontinuity or anything else right now, I'm actually going to skip this one. And we're going to start here. I want to know my points where f of x is equal to 0. So if I go back and I look at this problem, I only care about the numerator because the numerator determines my zeros. So I've got x squared plus 3x. Okay? X squared plus 3x. So I want to know, where do I equal 0 here? So I'm going to pull out my x value, and that's going to leave me with x plus 3, and that equals 0. And so then I'm going to solve each one of these. I've got x is equal to 0, x plus 3 is equal to 0, so that means x is equal to -3. So I have 2 numbers here I have to take a look at. So I'm going to take those numbers and I'm going to put them on a sign chart. So I've got this number line. I'm going to put my numbers here on a sign chart. I've got -3 and 0. Now, this 2 over here, this was for the denominator. I'm not worried about that right now, but I just left this on here because I'll use this example again later on. So now what I need to do is I'm going to ignore this 2 over here so it doesn't confuse you. Here are my -3 and 0. I want to pick some numbers that are before -3, in between here, and greater than here. I want to pick those numbers and I want to evaluate each one of those numbers. So I'm going to pick -4, -2, and 1. And again, I don't care about this right now. And then I'm going to evaluate that into my original function. And when I do that, what I'm looking for is, what is their sign value? I don't care about what their actual value is. All I care about is, what is their sign? So when I plug in -4, I get a negative number. When I plug in -2, I get a positive number. And when I plug in 1, I get a negative number. And so if you notice, I've got this negative, positive, negative thing happening here. So that means I actually have on from -10 to 10. Did I have that on here? Nope. So from -10 to 10, I have yes, there is at least one number on the interval that is a 0 by IVT. Okay. So if it's asking you, is there a number here on the interval from -10 to 10, you go through this process and you'll notice that I have sign changes. And since I have sign changes, the answer is yes, there's at least one number that will be on this interval that is going to be a 0. And we notice from from here to here, I have a sign change. So that's probably going to be a 0. And then from here to here, there's a sign change. That means that's probably going to be a 0. Okay. Now, the reason why we had to break it down this way is because this is such a big interval that sometimes you can wind up with a function that does something like this. So I have this function over here. Let's see if I can draw something. So if I've got this function and it does something like this, right? Okay. If I'm going from, let's say, this a value to this b value, I could look here and I could actually not have a sign change. But in all actuality, let's see if I can draw this again. In all actuality, if I draw this out like I want it to, I could actually have 2 sign changes, which means there's actually 2 zeros on that interval. But if I'm only focusing from here to here, and I look at that y value and that y value, there's no sign change between those 2 y values, but there is a sign change right here. So that's why you have to go through this process back up to here on this slide here. You have to go through this because if you don't do this, you don't know where to start. So you go through this and you want to know, where does my numerator equal 0? Well, this is where my numerator equals 0. So these are going to be my test points on this interval. Now, if you had gone through this and you've solved this, and let's say that this one right here was -13, well, that's outside of my interval, so I don't care about looking at that. I only care about looking at what's on my specific interval. Okay, so be aware when you're doing these, and if you're looking, like in this case, at your numerator, if I wind up with a number that's outside of my interval, don't care about that. Find something different to look at. Okay. So hopefully this wasn't too bad. Hopefully this answered a lot of your questions and everything. And, going forward, that if you do have questions, make sure you're sending me reminds. Make sure you're emailing me. Make sure, that you just get in touch with me somehow so that way I can walk you through it. Don't forget there's Delta Math there that's going to be able to help you if you're winding up getting stuck on something and you have extra practice problems. And then don't forget there's Khan Academy. They have videos, and plus some of this Khan stuff that you're doing right now should also solidify the stuff that we have just gone over. So if there's nothing else, it has been fun, guys. So I will talk to you soon. TTFN. Ta-ta for now.